Hello, and welcome to Physics Lesson 3.04, Vector Word Problems. We're going to work out a couple of, you guys would probably call them story problems that include vectors and show you some of the problem-solving strategies that go along with that. So we have a boat which has a speed of 12 meters per second in still water, heads directly across a river which has a current of 7 meters per second and is 480 meters wide. How long will it take the boat to reach the opposite shore? We always want to start these problems out with a diagram and coordinate systems. So let's say for both of these, well, no, you know what? I'm not going to do both. Let's draw a diagram first. So here's my river. Doesn't really matter how you orient it. And this is going to be 480 meters from here to here. $180 meters. And let's put my boat here. It's at the dock. Getting ready to take off. And it is going to have a velocity. So if the river was perfectly still, if we were going across a still body of water of 12 meters per second. But the river is not still, like most rivers. It has a current of 7 meters per second. Now, this is a 12 meter per second vector. So if I draw a 7 meter per second vector, it should be about 3/4 the length. Look, about 3/4, it might be a little long. Cut it off there and wipe this out. Your vector length should be proportional to what's happening. So 12 is longer than 7. This is 7 meters per second. So those vectors are not drawn too badly. And notice I drew them already head to tail. So I'm in a good position to maybe add these up. But the problem says, how long? So when we look for the question word, we've got how long. So we're solving for time. Well, okay, we have time, we have velocity. We know that velocity is change in distance over change in time. Okay, so this is probably an equation we're going to use at some point, and we're solving for this, but we don't know what the boat's velocity is because this current is going to be pushing the boat downstream. So the current's going to push the boat this way. So the resulting velocity, I'm going to put V and I'm going to do a subscript R. So this is the V of the current. This is the V of the boat. So if I add the vector for the boat velocity and the current velocity, that's going to give me the resultant velocity. Well, this one's pretty simple because I already have a right triangle. And I know that a squared equals b squared plus, wait, I said that wrong. Shoot. All of a sudden I can't say the Pythagorean theorem. C squared equals a squared plus b squared. I think I wrote that. Yeah. All right, if that's backwards, I apologize. All of a sudden, it's like 7 in the morning and the Pythagorean theorem went out of my head. But the long and the short of it is to find the resultant velocity. I'm going to take the square root of 12 squared plus 7 squared. And when I do that, I get that the resultant velocity is 13.89 meters per second. Okay, so that gives me my velocity. So over here, I can work this equation a little bit and keep the same color pen. I'm going to go with 13.89 is x over t. Now you might be tempted. You might say, okay, they gave me a distance, but wait a second, guys, that's the distance here. I need to know the distance here. Well, let's redraw another diagram. So I've got a displacement here. This is across the river. Let's switch vectors. 480 meters. I have the distance that the boat travels. This would be x for the boat. Well, I have to have, in order to solve, I'm going to have another piece of information, but check this out over here. Can I find this angle back here? Yeah, I sure can. If I take a tangent of theta is 7/12, that tells me that theta is going to be 30.3 degrees. So I could use my velocity vectors to find the angle because the angle is going to be the same. So I'm going to put this in as 30.3. Now can I solve for my distance? Yes, actually I can. I can say that the cosine of 30.3 is going to be the adjacent, which is 480, over the distance the boat travels. And when I solve for this, I get 555 meters. So now I can bring that up and put 555 here. And when I solve for t, I end up with 40 seconds. By the way, this was one of the problems on the review. There's 4 review sheets on your Google Docs homework. You don't have solution sets to those, only answers. That is the one place where I did not get all of the problems solved. So this will look familiar if you go in and work any of those. And also know that when you go in to do that, if you do any of those reviews, there are no solutions. So if you have an issue with a particular problem, email it to me and I'll do a video solution for you. I'm going to try to autofocus again. I feel like this is blurrier than usual. It might be a little better. All right, so let's look at the second problem. An airplane heads 35 degrees southwest with an airspeed of 370 kilometers per hour, while the wind is blowing 68 kilometers per hour at 80 degrees. What will be the velocity of the plane? I'm going to start off, I'm going to put these vectors on axes. Oops, that's probably going to be too far to the, take that off. Let's do this. You'll notice I drew this quadrant much bigger because if we're talking southwest, we're going to have north, south, east, west. So my vectors are going to lie in this quadrant. Right, the first one is 35 degrees southwest. So that means I'm starting at the west and I'm going south. So 45 degrees would be here. 35, I think, would be about right here. Now, this vector is going to be 370 kilometers per hour, so that has to be a pretty big vector. I feel like that's more like 40, but all right. And the value is 370 kilometers per hour. We have a wind that's blowing, and the wind is blowing 80 degrees southwest. I cut off my vector. I'm just going to pull my screen back. Now we can see the problem. Okay, how about that? So if this is going to be 68, that's going to be about what, close to a fourth. So this vector should be about a fourth of the length, and it's going to be at 80 degrees. It's going to be 10 degrees off the axis. So I'm going to say about right there and right there. 68 kilometers per hour, and that's a, whoops, I wanted the 80. 80 degrees. I don't want to use the 10, plus that would resolve me against the vertical axis. Okay, well, sometimes a good place to start on this. What will be the velocity of the plane? All right, before we go any further, I want a coordinate system. And in this case, I just want everything to be positive. So I'm going to make my coordinate system left is positive and down is positive. Now all my vectors are positive. And can I do that? Yep, I sure can. The true up will come when I find my resultant angle. So they want to know what will be the velocity of the plane. Well, the plane's flying this direction, but the wind is kind of pushing on the plane this way. So my resultant's going to be somewhere between the two. So the resultant's going to lie somewhere in here in the middle. If I wanted to try to draw these out head to tail, I would go this guy going this way. I've got this guy going this way. And so the resultant is going to be here. So I'm going to lie in this quadrant, and it's going to be with a greater angle than 35. So if I have something greater than 35 and less than 80, I know I'm probably in the right ballpark. You can't do anything with this. I approximated all of this. I approximated the length. In fact, I can tell right now this guy's too short. I approximated the angles. This can only give me just a general idea. So what are we going to have to do? We're going to have to resolve these vectors. All right, let's redraw my first vector. And you don't have to do all of this work. You don't have to redraw everything. Right now I'm doing it for clarity. And this has got a 35-degree angle. I'm going to draw my components in like this. This is 370. So that means, let's call this velocity of the plane. So we'll call this VP. So that means that VP, and remember I made these positive, is going to be 370 cosine 35I plus 370 sine 35J. So this guy is coming down. See if I can conserve some space here. This is the velocity of the wind. So I have VWX, VWY. This is 80 degrees. So velocity for the wind is going to be positive 68 cosine 80 I plus 68 sine 80 J. All right, I'm going to have to, I'm out of space, so I'm going to have to simplify these. Let's bring this down here. Let's go to the VP. I'm just going to write them VW. When I do my trig functions, I end up with positive 303.08 I, positive 212.22 J, and for the wind I get 11.80 I and 66 positive 66.96 J. So I add these together and I end up with my resultant velocity as positive 314.88 I, positive 279.18 J. All right, I'm going to slide my camera because I am out of space. So when what this means is the resultant plane velocity, these are my X and Y components. So if I was going to redraw this, I would bring out a horizontal. This is where you have to be careful because I made this way positive. So I'd want to bring out a, no, it's further up. This is one of the consequences of changing your coordinate system. So if I'm drawing out a positive 314, this is going to be VRX 314.88, and my vertical going in the positive direction. Now, I tried to make this, they're pretty close in size, so positive 279.18. That means that the resultant plane, VR, is going to be here. When I do my trig functions, so if I do VR is going to be square root of 279.18 squared plus 314.88 squared. And that's going to be 421 kilometers per hour. And then I'm going to have tangent. I'm looking for this angle. Tangent of theta is going to be 279.18 over 314. I'm going to end up with 41.6 degrees south of west. And that makes sense because we knew it had to lie somewhere between these two. This is not nearly as strong of a velocity as this is, so it pushed it this way a little bit, but it wasn't too far off course. So you'll notice that the speed with what we would call a tailwind is actually greater. We have to account for course correction. And you'll see that if you're on a flight, you'll notice if you go one direction across the country, usually if you go west to east, you make better time than when you go east to west. A lot of our winds blow from west to east. And so you get this tailwind and it increases your speed. You have to burn less fuel, you get there faster. All right, so those are two examples of how we would apply vector addition in word problems. You get lots of practice in sections. I think there's 2 sections of homework for this. I think 304 and 305 are both vector addition. So you can take a crack at those. Email me with questions. Thanks for watching and have a great day.